Okay, so today we're going to learn how to calculate cell potential of a galvanic cell. First you need to know the equation. The cell potential, or the E cell, is equal to the cell potential of the oxidation half reaction plus the cell potential of the reduction half reaction. So first step is you need to decide which element is being oxidized or reduced. So which half reaction is the oxidation and which one's the reduction. Don't forget your oil rig. Alright. If you are using the table to figure out which one is being oxidized or reduced, meaning you're using the potentials, the more positive the reduction potential means that it's more likely to be reduced. So, therefore, the one that is the least positive will be the one that is oxidized. Then you're going to write both equations as is from the chart. So remember, the chart has them all in reduction form, but you'll write it as is. Once you know which one is being oxidized, so the one that has the least positive reduction potential, you're going to reverse that equation and also change the sign of its voltage, because the E oxidation is equal to the negative E reduction. And so if you have the table for the list of reduction potentials, then you can always find your oxidation potential. All right, then you have to balance the two half reactions. Remember, the electrons transferred have to be balanced. So the electrons that are being put into the reduction half reaction have to equal the electrons coming out of the oxidation half reaction. Then you're going to add the two half reactions together and add the voltages together. Remember, we never multiply our voltages by the coefficient. Those voltage numbers do not change. So interpreting your table of standard reduction potentials is that the element with the most positive reduction potential is the one that will be reduced. The element with the least positive reduction potential will be the one that's oxidized. And remember, our reduction potential table is the exact opposite of our activity series. Metals that are highly active, that will replace other metals, are more likely to be oxidized. So they're going to be at the bottom of the reduction potential table. So let's do some examples. So here we have a reaction. It is not balanced yet. So we first need to figure out which one is our reduction half reaction and which one is our oxidation half reaction. We're going to balance it, put it together, and calculate our cell potential. So chromium is going from a 0 to a positive 3. If charge is increasing, that means you're losing electrons, so that's oxidation. So chromium is our oxidizing reaction. Iron is going from a positive 3 to a positive 2. Its charge is being reduced because it is gaining electrons that are our reduction half reaction. Alright, so let's add in our electrons. Remember that in reduction, electrons are reactants, and in oxidation, electrons are products. Okay, look here. We are needing to put in 1 electron for the iron to be reduced, but chromium gives up 3 electrons. We must balance the electron transfer. So we're going to take the top reaction and multiply it all by 3. So when we get our total, the electrons cancel out. Remember that this is also called your net ionic because our spectator ions have already been canceled out. They are not participating in the redox reaction. So our iron reacts with solid chromium to form iron with a new charge and aqueous chromium. Alright, next I want to know the E cell, so the cell potential. I have to look up those numbers on your chart. You have it, so take a look. Remember that there are different forms of oxidation and reduction. Sometimes they lose 1 electron, sometimes they lose 2, so make sure you're choosing the right one with the right number. So iron going from a plus 3 to plus 2 has a potential of 0.77 volts. Chromium, its oxidation potential we don't have right now, but we do have its reduction potential. it's negative 0.74 volts. But remember, the oxidation potential is just the negative of the reduction potential. So we change that sign, add them together, and we get our E cell, which is 1.51 voltage. Remember, a positive E cell means that it's thermodynamically favorable, so you probably want to use that battery. Okay, one more. Chromium. This time it's chromium going to chromium plus 3, but now we are taking iron and reducing it from iron 2 to solid iron. So again, as I mentioned, there are different forms of iron, and so you need to make sure that you check the right number on your chart. All right, so iron is being reduced again, chromium is being oxidized again. But this time, iron is gaining 2 electrons, and chromium is still giving up 3. So our coefficients that we need to multiply by, well, we need to multiply both of them. The top reaction must be multiplied by a 3, and the bottom by a 2. So this becomes 3, this becomes 3, this becomes 6, this becomes 2, 2, 6. All right, our electrons cancel out. We can write our total, our net ionic. I'll let you write that one in. And again, we're going to check our reduction potential standard chart and get that, well, iron going from plus 2 to solid iron has a reduction potential of 0.44 negative. And the oxidation, well, it's the same number as the one before, negative 0.74. We do not ever change the sign of the reduction half reaction because we are given the reduction potentials. That's what that chart is. But we still have to change the sign. So when we add those together, we still get a positive E cell. It's just a smaller voltage. So this is not quite as an efficient battery. All right, the other thing that you need to make sure that you know is how to relate E cell, so the cell potential, to Gibbs free energy, so thermodynamics. Remember, Gibbs free energy, if we want a thermodynamically favorable reaction or a spontaneous reaction, we want Gibbs free energy to be negative. In this equation, delta G is equal to negative N times F times E cell. All right, well, what does negative N stand for? The number of moles of electrons being transferred in your redox reaction. F is Faraday's constant, so it's always going to be the same thing, and the E cell is what you calculate. So basically, if you take a look, you are making whatever number you get negative. So if your E cell is positive, when you multiply it by your negative N, you're going to get a negative number, so delta G is negative. So when E cell is positive, delta G is negative, which means it's thermodynamically favorable. But if E cell was negative, then delta G is positive, and it is thermodynamically not favorable. All right, so let's try one. It's pretty easy. So using your standard reduction potentials, calculate delta G. Well, first we have to do is get our E cell and then plug it in. All right, so the E cell for that reaction, if you look it up, for the one being reduced is copper. So copper's reduction potential is 0.34. And then iron is being oxidized, and its reduction potential is negative 0.44, but we're going to change that to positive because we are changing it to an oxidation. All right, then add those two numbers together, you get 0.78 volts for your E. All right. We need to figure out our moles of electrons. Well, that's just basically how many electrons you're transferring. Well, how many electrons does copper 2 lose to become solid copper? 2 electrons. And how many electrons, how many electrons does copper gain? And then how many electrons does iron lose to become positive 2? It's 2 electrons as well. So our number for N is 2. Then plug it in, delta G is equal to negative 2 times Faraday's constant, that's a really big number, 9485, and multiply it by our E cell that we just got, 0.78 volts. Well, you don't even have to calculate it to know that this is thermodynamically favorable. It's going to give you a negative delta G. But if we want to know what our delta G is, we plug it into our calculators, we round to sig, and the units cancel out and leave you in joules. So it's negative 150,000 joules is our delta G, so it's thermodynamically favorable. All right, that's it.